Okay, let's start. Do you have any questions? All right, so we were talking about sum of independent random variables last time. Let me see. So 6.3, sum of independent random variables. Okay, so we discussed this last time, right? But basically, if you have x and y as two continuous random variables with densities f sub x, f sub y, then right, the density of the sum, right, will be the convolution of the densities of the individual terms. Okay. Now, I mentioned that, so this is just a formula, right, from the textbook. And this, right, comes from writing down what probability x plus y less than equal to a is. And then you develop that, right, until you, well, you develop that and then you differentiate this expression with respect to a, and you get that, okay? And so I mentioned that basically this formula doesn't take into account the support or the actual limits, right, that you have to impose when you encounter a particular problem, because basically it's just developed in the abstract, right, without taking into account what x and y can be. So in practice, right, when we have like an actual, distributions, like x and y are independent uniforms 0 to 1, right? Then it's better to just redo the process and rederive, right, the density yourself, not relying on the formula. I like the approach better because it can show you, right, what the thinking process is, and you can detect if there's any error, right, that you commit in between. For example, right, probability x plus y less than equal to a, and then you look at, right, basically if x, y are uniforms 0 to 1, then you have a square, right? And you have two cases, either this case, this is x and this is y, right? Or this case, right? And if this is the case, right, this is x plus y equals to a. And so therefore, right, this is when y equals to 1, so x is equal to 1 minus a. So a minus 1, right? This part right here is a minus 1. Of course, right here, right, this is a bigger than 1, right? This is a less than 1. And so this part is a minus 1, the whole length is 1. So therefore, this part is 1 minus that, which is 1, 2 minus a, right? And so the probability, and here, right, I guess I did not mention this explicitly, but when you have something like a uniform distribution, and of course, right, then x and y together, because they're independent, will be uniformly distributed on a square. Then basically, because when you take a double integral, you just integrate one, right, the x dy over any region. You're looking at the area of that region. So therefore, you just might as well jump into the calculation using the geometrical consideration, meaning you can just use the area, right, that you're looking at rather than doing the double integral. A double integral is useful or is a must if the density change, right? The density changes from region to region. But if the density is constant, then looking at the area itself using geometrical argument may be easier to do. For example, right here, we can easily see that this is the area, right? Which is a square over 2, if a is between 0 and 1. And then this is the area, right? Because it's less than a, which is 1 minus that area. So like that, right? And then, sorry. And then, so the density is a and 2 minus a. Okay. So that's it, right? And that doesn't even use or does not even need to use, right, the convolution in any way. The convolution formula can be used correctly if you know how to use it correctly to get to the right answer, but you need to know how to use it correctly. And as far as I'm concerned, whichever way you want to do it, that's fine. But the reason why I don't favor this approach is because it hides, right, all the process of thinking, and is useful in the abstract if you just want to say, okay, the density of the sum is so and so. I know the abstract formula, so I can do work with it. But in practice, right, it's probably easier, or it's probably more informative if you just start a process right from the beginning. But let me point out, right, how the calculation would go if you try to use a formula correctly, right? And so you try to look at, right, f sub x of a minus y, f sub y of y dy. And the thing to remember then, right, is that the densities have support where they are equal to non-zero, and outside the support there will be zero, right? So in particular, right, the argument for the density of the uniform must be between 0 and 1, right? So therefore, we have the requirement that and, right, both this must hold in order for the integral to be non-zero. Now, this, of course, right, means a less than or equal to 1 plus y, and then y is less than a. Okay, so both of these must be satisfied. And so immediately you see, right, there are two possibilities. If a is less than 1, then automatically this is satisfied because y is between 0 and 1, and we only have to look at this part. But if a is bigger than 1, then this is automatically satisfied, and we only have to look at this part. And that's why, right, there is a division of the range of a between 0 and 1 and 1 to 2. Well, I'm saying this because I have the benefit of hindsight, meaning that I have done the problem from scratch. So I know that that's the natural division of A, right? If I were to do this question using the formula and just having symbols staring at me like this, then yes, I might be able to figure out that A, the 1 is the natural division point of A, but it won't be that easy, right? I might make a mistake here and there, and then go back and then refigure things out. But anyway, right, if you see that A is the natural division, sorry, 1 is the natural division point of A, right? So between like this, right, then for example, then we need 0, right? If A is between 0 and 1, then these two conditions together is this. Then, right, the integral is the integral from 0 to A, right, of this. And of course, they're both 1s, right? So that's just now, but if A is between 1 and 2, right, then as I mentioned, this is naturally satisfied. We only have to look at this. Or y is from A minus 1, right, to 1. And of course, they're both 1s. So that's 2 minus A. Okay. So once again, the formula works, it's correct. But whether or not you find out the right information to plug into the formula, I claim it's not easy to see. But right, in the end, it's up to you to pick whatever correct approach to use. Any question? All right. So let's take a look at some of the homework problem. So I think here's question number 6.13. Two people, right? As this says, a man and woman, doesn't matter. A and B. So let me say this right. A arrives at a location uniformly between 12:15 to 12:45. B independently arrives uniformly between 12 to 1. So these are all PMs. Find the probability that the first to arrive waits no longer than 5 minutes. So these are one of those questions where, right, you need to formulate the question in terms of mathematical in mathematical terms, right? So we have something like X, right, which is the arrival time of A, let's say, which is a uniform, right, from 15 to 45. And Y is the uniform from 0 to 60, right? Now, what are we looking for? And they're independent. What's the question asking for? In terms of X and Y, what does this mean?
B arrives in less than 5 minutes when A arrives, and A arrives in less than 5 minutes when B arrives.
Right, but that's still a little bit English, right? What's the mathematical expression?
The probability of B arriving in 5 minutes, given that A arrives, plus the probability of
There's nothing conditional here, right? There's no given. There's not an if here. No. And yet again, right, it's still in English. What I mean in mathematical terms is in terms of X and Y. Purely mathematics, because you understand, right? If we mix English in here, we won't be able to perform calculation. Do you see that it's just really about X minus Y absolute value less than equal to 5? Right? So that's what I mean by, right, translating the statement into mathematical expression. Because then, right, of course, here this will be something like, if you will, Y minus 5 less than equal to X less than equal to Y plus 5. That's correct. Or you could just jump to here right away. Doesn't matter. But to me, this is easier to see, and is correct beyond a doubt, right? Because two numbers, if the absolute value is equal to 5, they're within 5 of each other. So, right, whoever arrives first doesn't have to wait more than 5 minutes. Okay. Now, as in how we find this actual number, what's the best way? The best way is, again, geometrical argument, right? We're just going to draw the picture. So $15, right, to 45, and then 0 to 60, right? So it's uniformly within this rectangle, right? And you have y minus 5 equals to x. Sorry, I mean x in terms of y, because we all kind of used to think of it in that language. Right? And y equals to x minus 5 is a line with, intercept minus 5, right? Which, when you come to here, when x equals to 15, is 10. When you come to here, when x is 45, is 40, right? So that's the line. And then, of course, the plus 5 is going to be 20. And then to 50. Right? And what are we asking? We're asking for the area of this band. What's the best way to find it? I mean, it's the relative area, right, of the band over the rectangle. So what's the best way to find it? You see, you can do a double integral, right, from here to there, from there to there. But for me, I think, again, you don't have to follow it this way, right? It's up to you to whatever approach that gives you the correct final answer. For me, I kind of want to use the geometrical argument that basically the area, right, of parallelogram, right? Let's do it this way. I believe is base times height, right? So the base is 10. The height is 30, right? And then divided by, so this is the area of the parallelogram, right? Divided by the area of the rectangle, which is 60 times 30. So the answer is 1/6. Any question? Okay, so follow up on this quiz. Quiz 2. What's the probability that A arrives first? Again, right? Formulate this in terms of mathematical symbols and then solve it maybe geometrically, or should be in this case, right? But what is it? So A arrives first is probability that X less than Y, right? So if you draw the line x equals to y, right, then x less than y is to the left of that. So let's see, right, if x is equal to y, it's 15, 45, right, and it'll cut at 15, and it'll cut at 45, right? So this is 60. So we want the area to the left of that, right? Because x less than y. So equals 1, right? Which is what? The area of the trapezoid, right? Which is 60 minus 15 is what? 35, right? Okay, let me say this. $35 plus 15, right? The sum of the two bases times the height over 2, right? The height is 30. And then you divide it by the area of the rectangle, which is 60 times 30, which you see is just 1. Again, right, the point here is about translating an English expression into mathematical language and then translate that into some sort of geometrical consideration. One thing, right, again, I emphasize that this is a convenient approach when we have uniform distribution, right, jointly uniform. If you have something like actual densities where things change, right, from one location to another, then obviously, right, area won't work, right? Just think of this as the mass. The relative mass of this piece is going to be the area of this piece over the total area because, right, the density of the material making up the whole piece is the same. It's constant everywhere. But if the piece is somehow a little bit heavier this way and then less heavier that way, then it won't be an area consideration alone. Okay, any question? All right, so this is also to point out, right? It's sort of this question, I think, right, even though it doesn't ask for it explicitly, also falls in the topic of sum of independent variables, something along that line. Why? Well, here you have x and y independent, right? And you have x minus y. I mean, you take absolute value, but why? Because, right, you can look at x and minus y, right, as independent variables, random variables. So, and you see, right, there's no formula involved here. You just have to consider everything from scratch. But it is part of, right, the big topic of, let's say, sum of independent random variables. So the follow-up question, right, would be, it says, you know, if after you, so this is question number 14, after you read carefully, it talks about an ambulance and an accident location, which are uniformly distributed along the road of length L, and they're independent of each other. So that's all there is, but you know, the book goes on and on, but that's really it. They ask for the distribution of the distance between A and B. Let's just say between A and B. So what are we looking for and how do we do it? So here we're looking for, so if we let X, right, and Y being uniforms 0 to L, right, and they're independent, then you're looking for the distribution of Z, which is the absolute X minus Y, right? Almost exactly as the above, but now we're kind of going to the distribution question in general. So what do we have? Oh, where do we start? Would you want to use convolution here? You want to use this formula? Well, here in particular, I think the formula is a bit useless because, well, the minus is easy to take care of, but it's harder to see how the absolute value, right, will fit in here. But on the other hand, right, like I pointed out, it's really just about the same approach. So you start with probability Z less than equal to Z, right? And then you plug in the definition, and then you work out the expression. Okay. And then you have to compute this somehow. And here, right, I would, you know, draw a picture, right? So you have a square, right? Length L. And you have something with intercept minus Z, right? And then something with intercept Z. Correct? And you want to look for the area in between. Well, so I guess one thing I did not consider, which is very important, right, is what? I should look at the support of Z, right? Big Z, because that will influence what value small z I plug in here, right? What's the support of big Z? What values of little z are relevant here?
Negative L to L.
Wrong.
Oh, L, 0 to L.
Correct. Right. what that means is, right, Z is going to be really between these parts anyway, right? There's no such thing as A bigger than 1, blah, 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 like this one, right? And that's why the support consideration is there, right? We're pretty sure that this picture is the only picture. Z only goes from 0 to L. All right? So it's that area, which is what? Which is 1 minus the relative area of these two triangles, right? But they're really symmetric, so we just have to do area of one rectangle, triangle, which is what? L minus Z, right? Which is right. So the PDF is 2 L minus. Any question? All right. So next, let's take a look at question number 24, which says that you have independent trios. With K plus 1 outcomes, right? 0 to K. Yeah, think of it as rolling a dice, really, right? 1 to 6, or if you include 0. So it's like rolling a K plus 1 dice, but these are not equally likely, right? This is not fair dice. Okay. And then you have a random variable that's going to be very popular in stochastic process consideration, which is the first time to something. So and it's a number of trials until the first outcome is not 0. And X be the value of the outcome. Meaning the outcome, right? The first outcome, that's not 0, right? After the number of trials. Okay. So question A, find probability n equals to n for n equals to 1. What is this? Well, what kind of random variable is n? Does it fit into any family that we know? Well, you see, right, because the trials are independent, N is really waiting for a success, right? But what kind of success? Success is something non-zero, right? So success is 1 minus P0. Therefore, probability n equals to N is P0 raised to the N minus 1 power times 1 minus P0. Okay? Question B, find probability X equals to J for J being equal to 1. Or, you know, the textbook says J from 1 to K. Notice, right? The possible values of J does not include 0 because, right, X is the value of and then the number of trials until first one does not 0. So what is it?
EJ over 1 minus PO.
Right. So that's correct, right? It sounds like PJ, but if you think carefully about it, it's not correct because the sum of PJs together from 1 to K cannot be 1. The reason is you already know. So it's sort of conditional here. So X is some kind of conditional distribution, which is the topic of the next section. But basically, when you look at X, you already know that X cannot be 0. So therefore, you have to divide it by, right? It's like conditioning on the fact that the random variable cannot be 0. So does it make sense? So it's really this kind of where Y is not, so where Y is a regular, right? Outcome of a trial. So X is exactly like that. X is Y, condition Y not equal to 0. That's why it's like that. Any question? C. X and N independent. X. Well, how do we answer this question? We have to look at the joint, right, of X and N and see if it's the product of the marginals, which is what we found out above. Well, what's the joint? What is this probability? Well, this is the probability of a sequence of zeros, right? Of a sequence of length n, where you got a bunch of zeros, and then you get j. Correct? So it will be p0 to the n minus 1 times pj. Which is p0 to the n minus 1 times 1 minus p0 times pj over 1 minus p0, which is, of course, and since this is true for all n and j, yes, they are independent. Any question? So we won't write down the next question, but they ask if you're surprised, right, that n and x are independent. Or I guess the question is more like, is it intuitive to you that n and x are independent? And well, the reason why we don't write this down, and the question also, right, is because it's just a subjective answer rather, right? Because if you ask someone if it's intuitive that so-and-so is true, well, either yes or no can work, right? Because it just depends on how the intuition works. But let's see what they're after here with this question. The point is, right, when you first look at this question or hear about the question, hear about the problem, probably, again, I'm talking about my subjective, right, intuitive feeling, it seems like they're not independent, right? And where does that come from? It just comes from the good old rule of thumb, right? That says if two random variables somehow have some connection, right? If they influence each other, then they're not independent, right? Again, this shows you how far intuition can go and how, let's say, dangerous it can be if, you know, your intuition is not precise enough, right? It's not clear enough. So yes, rule of thumb, right? Random variables that influence each other or have connections are not independent. Well, in view of that, why is it then that they're independent? Well, so this is, again, right, this explains why you need calculation to back up your intuition, or you need calculation to clarify, right, your intuition. So in point of view of this calculation or looking back on things, you see that intuition is not precise enough, because, right, influence here really means, right, that the value of one random variable does not influence the value or the likelihood of the other random variable. But from that point of view, you see, right, then yes, they seem to be independent, because it doesn't matter what value of n is, right? N can be 1,000,000, right? If I tell you, right, that n is 1,000,000, does it change how you predict the value of x in any way? I think the obvious answer is no, right? Because if you know that it takes 1,000,000 trials until you obtain the value, right, that's non-zero. That doesn't mean that you know what that value is. I mean, you know it's non-zero, but beyond that, you don't know anything. So, right. Are we okay? So again, this is in hindsight and with calculation, blah, blah, blah. And I don't claim that, right, anyone's intuition works like mine or anyone's intuition works like each other. But that's why this answer is subjective. But you should and build your own version of how you tend to think of things as independent. And you should always back intuition up with calculation, right? That's probably the only message here. Any question? All right, so I guess let's continue with the next question. We have A, B, and C are independent uniforms 0 to 1. This is question number 626. Find the probability that the quadratic has all real roots. So how do we answer this question? So first of all, right, we need to translate this question into some statements involving A, B, and C. Because A, B, and C are the random variables, right? So what would that be? When is it that a quadratic has all real roots? When the discriminant is not negative, right? Or is non-negative. The discriminant is b squared minus 4ac non-negative. So that's pretty straightforward, right? We translated let's say an English statement, right, into a mathematical expression in form of A, B, and C. But what's next? How do we calculate this? Or at least, right, if you can't get the direct answer out, it depends, right? It doesn't have to. If the question is complex, at least what is the process? Do you have the process in your mind that you will for sure get the right answer if I give you enough time? What is the process? So let's ask, right? Is a geometrical consideration in the air here? Is it possible for a geometrical argument? Well, the answer is, in theory, yes. But first of all, we recognize this is a three-dimensional question, right? Because you have A, B, and C. So you're looking at a cube, right, of length 1, a unit cube. And the shape you're looking, right, inside that cube is the shape of b squared equals to 4ac, right? And you know, you can look at A as the X coordinate, B as a Y, you know, it doesn't matter, right? I don't recall what geometrical shape this is, even though I've taught calculus, I think at least twice or something. Maybe a paraboloid, but that's not true because this is a product here. In other words, right, even though in theory, geometrical argument is in the air, unless you really know what this shape is and the volume involved with those shape, that with this shape, I think, is really not an option. Okay. And if you look at the answer, if you know the answer, then nah, it's really not there, right? Because so no. But if a simple geometrical argument is not in the air, then what? Then triple integral you go. Okay. So you have to do a triple integral of the, well, okay, I won't. Triple integral of what? So the joint density is 1, right? Because it's a unit cube. The challenge then is to decide the limits. So that's the process, at least so far. Can we see what the limits will be? So, right here, the region is clearly some sort of region where b squared is bigger than 4ac. And of course, right, a is between 0 and 1, b is between 0 and 1, c is between 0 and 1, right? So it seems like it's going to be something like dB. Notice I do dB first, right? The ADC. The reason is because B is bigger than 4AC, right? So that means B itself is bigger than 2 square of AC. Notice here, I already utilized the fact that A, B, and C are positive, right? So that when I take a square root, I don't have to involve absolute value. Is this correct? Because you understand, right? If you get the wrong limits, your probability will be wrong. Is this the right answer? Or the right limits? Well, the answer is nah. It's not the right limits yet. The reason is, well, the B is all right. The B is correct. But the A and C are not really that. Here you say the A and C can go anywhere right within a unit square. But notice, right, the lower limit here is 2 square of AC. It is a lower limit, right, because B, right, is between 0 and 1. So B, the upper limit of B clearly is 1. However, right, if you take two numbers between 0 and 1, A and C, take a square root of that, whatever, it's still between 0 and 1. If you multiply by 2, clearly, right, some combination will be more than 1. Right? In other words, we have to not look at the region of the square here, But the region here will be some region where 2 square of AC is less than 1. Right? Which is what? Which is same thing as saying A times C is less than or equal to a quarter, or A less than or equal to, let's say, 1/4C. Well, what does that mean? That the triple integral now will be 1 dB dA dC, where B runs from 2 square of AC to 1, A runs from 0 to 1/4C, and then C runs from 0 to 1. Is that the limit? The answer is still no. It's still not right. Why? Well, why here is you have to really look at the 2D region of A and C, right, to see what happens. So it's between 0 and 1, right? And the A equals to 1/4C is hyperbola, right? That looks like this. Where clearly this is, right, when C equals to 1 and A equals to a quarter. And when A equals to 1, C equals to a quarter. And you're looking at the region to the left of this. So you're looking at this region. And you see that clearly this region is not about A going from 0 to 1/4C. Right? So what I mean by 1/4C is 1/4 times C, right? Because you see this region is rather a bit annoying. Right? It's like that. So it's actually three, at least as far as I look at it, there are 3 regions here we have to look at. There's this limits, and this limit. So in other words, right, you will have 3 integrals here. The first one, right, so dB, dA, dC. The first one runs from 2 square of AC to 1 for B. Then A runs from 0 to 1. And C runs from 0 to 1/4. So that's this part. The second one, dB, dA, dC. B runs from square of AC 2 to 1, but A, right, runs from 0 to a quarter. And C runs from a quarter to 1. You have to be careful, okay? Because even here, if you're careless and you say 0 to 1, then what you have effectively done is you double count this square right here. So it's not 0 to 1 here, it's a quarter to 1. And that's this part. Now finally this part. It will be square root 2 square of AC to 1 dB dA dC of so A runs from a quarter to 1/4C, and C runs from a quarter to 1. Okay. Now I do allow for, right, a easier approach to this triple integral to calculate this. in fact, if you have some suggestion that gives the same answer as this, which is something like 1/6 log of 4 plus 5/36, if I recall correctly. I might be wrong. But you see, because of the log of 4 here, right, I doubt that very much that it's a geometrical consideration, because no geometrical shape that I know of has a volume that involves natural log. Anyway, right? But if we don't see anything interesting going on here, then triple integral is the way to go, or integral in general is the way you go. And deciding the right limits is part of the course, right? Again, I'm not saying it's easy, straightforward, not mistake prone, etc. But that's what we have to do if we want to work with joint distribution in general. Any question? All right. So now let's go back to the topic of 6.3, sum of independent random variables. But so here, 6.3, the textbook rather mentions quite a bit of things. Let me just tell you what I'm interested in covering from here. The topic that the text has, let's say, 3 topics I'm interested in. Sum of independent binomials, sum of independent normals, and sum of independent Poisson. All right, and there are more. The textbook approach all these using the convolution approach or whatever, that one that we just did, right? This one. Meaning that they use the distribution approach, right? Distribution function approach. What I want to do here is I want to do a different approach, which is actually much more common and much easier and much more powerful. What I want to do is called the moment generating function approach, which if you look at the text, so moment generating function from now on will be referred to as MGF, just to, not keep saying a long word. MGF is the topic of 7.7. All right. But this is the right place to discuss it, because sum of independent random variables is one of the reasons why we look at MGF, or we study MGF. And you have all the necessary knowledge to look at MGF anyway. So in some way, we're doing things out of sequence, but sequence is just one way the textbook likes to present the materials, okay? So we want to kind of go to the MGF, right, of 7.7, introduce it first, and then see how it's used, right, to look at sum of independent random variables. So, and I'm going to mention MGF enough. Of course, more aspects than just this. But if I find something that I forgot to mention my MGF. We're gonna mention it later on, right? But for now, I'm just gonna cover MGF enough with a view of doing that. But I'll do more. I do general moment general function too. So here, so the first thing is right, is a definition. The MGF of a random variable x, okay, is by the definition is phi sub x at a value t, which is expectation of e to a tx. Okay. So something to mention here. First of all, the MGF is a deterministic object. There's nothing random about it, right? It's a function evaluated at a value. All right. Maybe the first thing that students may ask is, okay, at what value? By that question, I think they mean the domain of the MGF. Well, the answer is, well, you just have to look at the calculation to see what the appropriate domain is. Because basically, this is, okay, so let's write it down, right? If you have a discrete random variable, then this is just the sum of all possible values of x of e to tk, probably x equals to k. But if x is continuous, and this is the integral e to tx density. And here, right, is this expression that I want to mention, because this, I mean, depends on the version, is connected to the Laplace transform of the density. Well, if you take some course like 421, then I believe Laplace transform, the fourth direction has a minus sign here, and it's 0 to infinity. But whatever, it's sort of like connected there, right? So depends on how you look at the defined Laplace transform. But the point is, right, if you ask for what value of t, then it just depends on what t you can plug in here so that this integral converge, or this sum converge, right? So, but it's a deterministic object evaluated over an appropriate domain of t. Okay. So let's take a look at some example. Where are we? Quiz 5, right? Quiz 6. Suppose x is a Bernoulli. Find the moment general function of x. Well, what should it be? So when someone asks for the moment general function of a random variable, it's just a disguised question to ask for the expectation, right? The Bernoulli can take on two values, right? 0 and 1, with probability 1 minus p and p, right? So this e to t times 1 times p plus e to t, sorry, e to t times 1, yeah, t1, t which is t. E to t times 0, which is 1. That's it. That's the MGF of a Bernoulli. Any question? if we have a binomial NP, find the moment chain function. Well, again, right? It's still the same question, but a different distribution. So this will be, right, the sum of k from 0 to n, right? E to tk, n choose k, p to the k, 1 minus p to the n minus k. Well, what is it? How do we compute this sum? Well, we compute this sum, right, by trying to utilize the binomial formula somehow. And you see that, right, one straightforward way to do that is to group the e to tk into the p, right? So it's something to a k power. Because this is exactly the binomial formula, right? And choose k, a to the k, b to the n minus k, which is a plus b to the n, right? All right. Any questions so far?
Professor, just to reiterate, what did you say T represented or like was?
Good question. Nothing really. It's a dummy variable. How to say this, right? So here, when you integrate out, right, something like this, the x part is integrate out, so it has a t part left. So if you want, it's part of a mathematical technique called something generating function, but so basically you have a sequence of numbers, but then you don't want to look at it as a sequence, but you want to introduce a variable that sort of make into a function. So I forgot what it's called, but yeah, you make a function out of an object, right? Somehow, I think it's something generating function, but basically that's the idea here. You have a static object, which is not static, but you have a density, but then you want to transform it, make it to a function of t. All right, why you wanted to do that? Right, that's one of the deep secrets of the universe, right? Basically, when you do that, some interesting properties happen. And so, yeah, so in a way, right, that's Fourier series too. You transform something from a domain to another domain, but with Fourier series, it's kind of more clear. You transform something from a space domain from a time domain to a frequency domain. Here, you transform a function from the x domain to a t domain. So there you go. T doesn't have a physical interpretation. It has a mathematical role. But unless or until you have done something like Laplace transform, the mathematical properties or the usefulness of it won't be clear. Well, we'll try to point out something here in this chapter too. But to answer your question, it's all about mathematical usefulness. I don't think there is a physical interpretation for T. For Fourier series, yes, it's about time to frequency. Laplace transform, I don't think so, as far as I know.
Thank you.
Any other question? All right, so I want to draw your attention to these two structures. It's not a coincidence that they are similar somehow. They share something in common. We'll be more explicit about that, right? But let's talk about, well, I guess right on cue about the question of T, etc. Let's talk about the use of MGF, right? Because if this is the first time you see something like this, you might think it's a very funky object, and yeah, I would I have nothing right against that. Yes, it looks very funky, right? Why do we even look at some object like that? Well, the answer, of course, lies in the use, right? So the first use of it, which is something people keep mentioning, but I don't find it used in practice very often, is the word moment generating. It can generate the moment for you. How? Well, so you have, right, that by definition is expectation of e to tx. Okay. Again, keep in mind that t is a fixed value, a constant. X is a random variable. But let's say that I want to differentiate, or I want to look at the derivative of this function with respect to t. Well, what do I get? Well, it's this, right? Now, this is one of those moments where you might think the next move is entirely obvious or whatever, or you might think that the next move is full of magic. Your pick. But we can exchange differentiation and expectation. Okay. Not always true under certain condition, but here, let's say that we operate under those cases where the conditions are satisfied. Then what? Differentiate this to t, right? T is, so x is a constant in this case, so x goes down. So that's going to be e of x e to tx. Well, what can we do with this, you ask? Well, we can plug in t equal to 0, which will give us expectation of x. So, right, because e to 0 is 1. So the derivative of the moment generating function at 0 gives you expectation. Well, can we continue? Well, you bet. If you take the second derivative, which is the derivative of the first derivative, right? Meaning you differentiate this expression. And again, right, assuming you exchange integration, you exchange expectation and differentiation. And that's that, right? But again, x is a constant. So the only thing, so x is a constant, so it comes down. So it will be x squared. How do we get rid of the t? Well, we plug in at 0. So that's how it generates the moments for you. You keep differentiating with respect to t and keep plugging in 0, you'll get the moments. So I have to say this, right? In general, you may not be able to plug in 0 directly. because 0 might not be in the domain of the derivative, you see, you end up dividing by t. So in general, if the limit, so if the expectation exists, okay, if the moment exists, then the limit as t goes to 0 of the nth derivative will be the expectation of x to the n. Okay. The reason is, right, we have mentioned some distribution where the first moment does not exist, like the Cauchy. So this is how it generates the moment, and how it justifies the name that is moment generating function, right? And possibly in some corner of the universe, like of mathematics, I believe that, right, these techniques are maybe one of the reasons that the Laplace transform is considered, because it kind of gives you an indirect way to evaluate the integral of x, f of x dx. Why, you ask? Do we have to go through such complicated route? The reason is maybe because the direct route is not easy. So you kind of use an indirect way, which is easier. But this is why I say in practice, I haven't found this super useful, because differentiating this function is a pain. The more you go down the layer, the more terms you have, the more products you have to deal with, etc., etc. But enough, right? Let us demonstrate, okay, the result, and then we will leave it at that. And if you have to ever do this kind of question, then you just remember that the result is true. You just do it in your particular case. But let's demonstrate it for the, you know what? Let's demonstrate for the binomial. Okay. So x is binomial NP, right? What is expectation of x? Well, expectation of x is n times p, right? Well, let's see if that works with moment generating function. So this is the moment generating function, right? So if you differentiate it with respect to t, you get n p e to t plus 1 minus p raised to n minus 1, right? Times p. Sorry, times p e to t, right? Because it's chain rule, right? So if you plug in t equal to 0, what do we get? Well, if you plug in p equal to 0, t equal to 0, you got p plus 1 minus p in this expression, which is 1, right? 1 raised to n minus 1, and you got, that's exactly n times. Okay, so far? But we're going to do just one more to show you how not very practical this is in at least in regular application. In the abstract, this is very beautiful. In the abstract, you can probably write down a lot of moments using this formulation. But in actual calculation, maybe not. Well, expectation of the second moment of the binomial. Well, remember, the second moment is the variance, which is np1 minus p, plus expectation squared, which is np squared, right? So how does this work with the MGF? Well, so if you look at the second derivative, and by the way, right, it's here, it's not here that you differentiate, right? Because there's nothing about t in it, right? It's this one. But notice here, when you differentiate with respect to t, you have to deal with product rule, right? Because you have two parts of t, and that's exactly what tends to happen. The more you go down, the more complicated the expression will be. Well, let's just do it one more. So this will be, right, if you do product rule, then if you differentiate with respect to this part, you got n minus 1, right? N minus 2, you pick up exactly this part again, so it's squared. And if you differentiate with respect to this part, you just, of course, get e to t. So actually, this is not too bad here. It's because e to the t differentiates to e to t. So if you plug in at 0, what do you get? You get n minus 1, right? You got p squared. You got n. Oh, sorry, this is p here, right? You got n times p, right? Well, is it this answer? So you got np here, right? That's this np. Oh, wait, hold on. Yeah, np minus np square plus n square p square, right? So that's np here. And n square p square is this part. And then minus np squared is this part. So yeah, it's correct. Okay. But like I said, it's there in the theory, and you can verify with any example you want. But in practice, I haven't seen people calculate moments using this approach as much. Who knows? Any questions so far? All right. Now let's come to the use of the MGF that I consider as the use of MGF. I mean, this one is fine. It's there. It's mentioned in all textbook. Just don't find it that popular, in my experience. But the second one definitely is. The second one is about to identify a distribution. And by the way, right, this is exactly where you will see that if you look up on Wikipedia on any distribution, right, you type in, I don't know, chi-square, binomial exponential, blah, 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 right? Then Wikipedia or any kind of reference source will give you the distribution, meaning the mass, if it's a discrete, the density, if it's continuous, may give you a few moments, right, the variance. But one thing they always will give you is the MGF of a random variable. Look at this complete or standard description of a random variable will almost always include MGF. All right, so the reason is something along this line, to identify a distribution. Well, so what's the sort of the technical language to describe it? The technical language is the following, which is a little bit weird, but if you have two random variables that have the same MGF, then they must be the same distribution. Okay. And let's clarify this to begin with. This is the superscript D here means having the same distribution. Doesn't mean they're equal, all right? I mean, here's an example that's very easy. If you look at XY uniform 0, 1, let's say they're independent, then X and Y are the same in terms of distribution. But clearly, right, X and Y cannot be the same in general because they're independent in terms of values. Okay? So that's what we mean. If two random variables having the same moment generating function, then they're the same random variables, if you will. Now, if you ask why this is true, well, this direction is kind of obvious because you will take expectation of the same density or the same mass function. The reverse direction, right, is actually the property of Laplace transform, meaning it says that Laplace transform of our function is unique. So you can take the inverse Laplace transform and get back the function. There's no 2-to-1 map, right? It's 1-to-1 map. So from the domain of x to the domain of t, that's why when you go back, it's the same function. Okay. So that's sort of the use. Well, again, so what does this mean? So another example is like this. Suppose you have a random variable. I don't know where you got it from, but you tell me that, hey, I know that its moment-generating function is this. Okay. Then I'll tell you, well, you definitely have a binomial NP on your hand. That's it. Right? Like the only information you know is this. Nothing else. Then, but it still would be enough for me to say that what you're looking at is a binomial NP. Okay, so far? Any question? All right, but still you asked, right? So what, right? Why is it useful? It's useful in this scenario, and we're gonna just need some small proposition to show things. If you have independent random variables, and you look at the moment generating function of the sum, again, so now you see how it connects back to the sum of independent random variables, then it will be the product of the moment generating functions individually. So the MGF of the sum is a product of the MGF. So in this way, right, basically MGF of the sum is very easy to calculate, provided you know the MGF of the individual term. So what's the reason here? Reason is pretty simple, right? If you look at the expectation of this, which is by definition, that's an MGF. Well, right, it's gonna be e to tx, e to ty. But, sorry, I think when we do independent random variables, I forgot to mention this, right? But basically, expectation of a function of product of, or maybe I didn't mention this because it's in the next chapter, maybe, but let's mention this. Basically, it will be product of the expectations. Which is by definition. All right. I don't think this is surprising to folks in general, but let's prove it, right? Let's prove this part. But yeah, so that's that, right? So moment generating function of the sum is a product of moment generating functions because expectation of the product of independent random variables is a product of the expectations. So any question about this before we kind of prove this statement, which is going to be very quick. So let's do a detour, right, and prove this. If x, y are independent, then expectation of any function of x times any function of y will be expectation of that function of x times expectation of that function of y. Now, so this direction, again, I feel like it's intuitive to a lot of folks, and if it's going to be easy to prove. I'll give you something for free. It also goes back. As long as you check this direction for any function f and g. which is actually very hard. Because, right, it's not enough to check the function that this works for some function f and g. You have to check that this holds for any function f and g. Then you can conclude that the x and y are independent random variables. But the direction we're concerned with right now is this forward direction. So what's the proof of this? Well, right, you just kind of use the law of unconscious statistician. Let me say, let me deal with the continuous case, right? The discrete case is very similar. So expectation of this will be the double integral, let's say, right, of f of x, g of y, times the joint density, right? This is integral over the plane. But we know that x and y are independent, right? Therefore, the joint density is the product of the marginals. Sorry, this is little y. Well, what do you know? This is a function of x only. These are functions of y only. And a double integral, right? You can factor out. And then it becomes g of y, f sub y of y dy times f of x, f sub x of x dx, which is exactly expectation of f of x times expression of right, like that. So yeah, that's probably one of the beauty, right, of independent random variables. When you take any functions of them and you take expectation of the product, that's a product expectation, which justifies this move. All right, any question? Okay, so now, right, let's go to the real punchline of the part here, which is that so we know, right, so let's recall that if you have a Bernoulli P, then its moment-sharing function is P e to t plus 1 minus P. If we have a binomial NP, then its moment-sharing function is P e to t plus 1 minus P to the n. Right? I think once upon a time, I claim that if you have x1 up to xn, right, IID, Bernoulli P, then the sum has a binomial NP distribution, right? And I said this claim is pretty obvious if you just look at the meaning of it, because each individual xi's would tell you the success or failure of trial I, right? So the ith trial. So if you sum them up, that's a total number of successes in n trials, which of course is what the binomial is describing. So intuitively, or even in terms of meaning, this should be super clear. But let's try to do it in the mathematical way via the MGF approach. So the MGF proof would be as follows. Right, the moment-sharing function of the sum is the product of the MGF. But, right, each of these will be that. And of course, that will be the nth power of that. And of course, now, right, here's where we use this fact. Oh, sorry. If two random variables have the same MGF, then they have the same distribution. Here, the sum of the Bernoullis have exactly the same MGF as a binomial NP. Therefore, it has binomial NP distribution. That's a proof. Any question? Okay, let's do one more. Claim. If you have x1 binomial N1P, x2 binomial N2P. Notice they must have the same success rate, just different number of trials, and they're independent. Then x1 plus x2 will have binomial N1 plus N2P distribution. Again, you see this is along the line of the result of, right, sum of independent random variables. Now, once again, this is pretty obvious, I think, right? Because again, total number of success in the first N1 trials, total number of success in the second N2 trials. And because they're the same kind of trials, right? Because they have the same success rate. I mean, not the same kind, but they have the same success rate. So you can just look at them as one big experiment with N1 plus N2 trials. Well, so that's the intuitive argument, which I think is completely fine here. But if you want to do the MGF approach, well, what is it? The moment-gen function of the sum is the product of the moment-gen functions. And of course, right, individually, they're like that, right, with N1 and N2. And you see, right, and this is exactly where you see we have to have the same P. Because if we don't have the same P, then this cannot be combined. But they're the same P, so we get N1 plus N2. And once again, this is the MGF of a binomial. Therefore, this has a binomial N1 plus N2P distribution. Okay, any question? All right, so let's do something a little bit less obvious here. What quiz are we on? Quiz 6, I believe, is it? Quiz 7, right? Oh, quiz 8, rather. Suppose X is a Poisson lambda. Find the MGF of X. All right, so what is it? So we have to look at, right, phi of X of T which is the expectation of e to tx, right? Which will be the sum, right, of e to tk, and then probably x equals to k, right, which is e to minus lambda to k over k factorial. K runs from 0 to infinity. So that's the definition. How do we simplify this sum? Well, we can simplify the sum, right, by combining the kth power, which is e to minus lambda e to t raised to k over k factorial. Well, e to minus lambda is a constant in terms of k, right? It can be factored out. What's left is this sum, which is, x to the k over k factorial, so it's e to the x, e to the lambda e to the t, which, if you combine, is e to lambda e to t minus 1. Any question? So here's a punchline about Poisson. If you have x and y, let's say x1, x2, as independent Poissons, lambda 1, lambda 2. Then the sum is a Poisson, lambda 1 plus lambda 2. Okay, so the strong caution here is that don't take this as obvious. Because, right, the cautionary example is if you sum two uniforms, you do not get a uniform back, you get a tent shape. And as I said, right, it's more like the norm than the exception. When you sum random variables, you go outside the family. So we've been presenting you with nice examples, because they stay in the same family, so it's easy to show. But this should not reflect, right, the reality of how random variables interact in any way. But what's the proof of this? When it comes to Poisson, I think we don't have any intuition about how to sum Poisson. I think, well, you can talk about incoming stream of one event, an incoming stream of another event, but I'm not convinced that somehow when they mix, they stay Poisson, right? I mean, at least intuitively, it's not clear. But you can do an MGF proof. So phi of x1 plus x2 at t is phi x1, phi x2, right? Now, each of them will have this form. Which you see, because exponential, right, of the product is a sum of the exponents, you do get which is, again, right, this form with lambda being lambda 1 plus lambda 2. Therefore, it's a Poisson lambda 1 plus lambda 2. All right, so we'll continue, right, with the normal on Monday. Friday, again, right, remember it's midterm 2. And same setup, right? First 35 minutes or so, whatever is office hours. The rest will be exam. All right, so I'll see you on Friday and then Monday.
So wait, what chapter is midterm 2 up to? Is it 6.1?
It's up to whatever that was covered on last Friday, which I said was what? What did we cover until last Friday?
I have 6.1 written down.
Okay, then it should have been 6.1 then. Yep. 6.1 it is.
Thank you.
Thank you.